So I have to set the sound to, so you hear them as well? So you're using headphones, okay, great. Echoes. Okay, so then let's start. So welcome to our third lecture in collective processes. And this will be the final lecture that is more methodological and technical. So today we'll talk about field theory representations of the kind of processes that we've been looking at last time. Let me just share the screen. Okay. Here we go. So if you remember the lecture, so you can see that? Great. So if you remember the lecture that we had last time, I gave a little introduction to the mathematics that is behind the description of stochastic processes. And we discussed two kinds of stochastic processes. Yeah, or not two kinds of stochastic processes, but two ways of describing stochastic processes. The first way that was associated with the name Langevin, that we already featured in the very first lecture, relied on deriving a stochastic differential equation that describes the time evolution of a single realization of such a stochastic process. And the alternative approach that Einstein applied for the description of Brownian motion was to derive an equation for the time evolution of the probability density itself. Yeah, that was the master equation. This master equation is not a stochastic differential equation, it's a deterministic equation, but it's typically highly dimensional and relies, as you saw last time, on some integrations over the possible states that you can jump into. And then for those of you who remained for the example section last time, you will have seen that these master equations, although they look pretty complicated, can be derived phenomenologically, actually, in most cases, in a very simple way. Yeah. So these are the two kinds of description, and why are we not completely happy with that? So there exist approximative, so both in general conditions, both of these kinds of equations cannot be solved. There exist approximative methods that we discussed last time, for example, the Fokker-Planck equation, that was an approximation for the master equation. And these approximative methods, they work in certain special cases. Yeah, the Fokker-Planck equation, as you remember, the derivation relied on making strong assumptions on how these jumps in state space look like. They're very nicely behaved, and these jumps are very small, and that you effectively rely on a very large system size. And in other cases, there are no approximative methods at all. So what field theory does for us is it gives us a flexible framework, a general and flexible framework that allows us to describe a large class of stochastic systems. And it is even, maybe if you remember from statistical physics or quantum mechanics, it's so general that you can apply it to a very diverse set of systems. So one thing is, for example, spatially extended systems. Yeah, as you can see on the bottom right. Yeah, so this is a system where the evolution or where the spatial information in itself is very important. Yeah, because you see here there's a chemical system. You see that here structures form. It's an example of what's called binodal decomposition. So here the spatial component is very important, and this has to be taken into account when you want to understand, of course, collective processes. Another example are nonlinearities in stochastic differential equations. These become, especially if they affect the noise term, become pretty hard very quickly. And another example is that I would have showed you last time, that field theory, typical approximative methods like the Fokker-Planck method or other kinds of expansions are not very suitable for rare events, for the tails of probability distributions. So in field theory, we have a general framework of understanding these rare events. And so there has been a lot of work on how to make approximations to these field theories that allow us to understand the tails of probability distributions. And very often these tails are pretty important. Yeah? So they're rare, but if you think about like a nuclear reactor or something like this, yeah, so these rare events are rare, but you want to know how often they occur. And there are a few theoretic methods that allow you to calculate the tails of probability distributions very nicely. So this is what we'll do. Yeah? And in this lecture, I want to show you how we can derive a field theory description for the Langevin equation, for stochastic differential equations. We'll be looking at very simple Langevin equation that doesn't have any explicit time derivative, that doesn't have multiplicative noise. And we can, nevertheless, in the framework of field theory, we can straightforwardly extend this methodology to more complicated systems. So we restrict ourselves to this very simple Langevin equation with Gaussian white noise that is, as last time, uncorrelated. So so the first step here is to discretize time. Yeah, and so we take the Langevin equation and we write it down in discrete time. And as you saw last time, or in the first, was this the fourth lecture already? Yeah, so 2 lectures ago. Oh wait, whatever. Yeah. So no, last time was stochastic processes. Yeah. So as you saw last time, the way we discretize stochastic differential equations, and I showed you that for stochastic integrals, is very important. Yeah. And in this case, we also have to discretize our stochastic differential equation in a certain way, which is called the Ito discretization. And but if we do that, if we discretize our stochastic differential equation in this way, the idea is that in principle, we can write down averages over any observable, that's here on the left-hand side, by some complicated thing that is on the right-hand side. So what is on the right-hand side in this equation looks pretty complicated, but it's not that complicated. So let's have a look at these different terms. Yeah, in the first term here, on the right-hand side, the red term, we just integrate over all possible realizations that a stochastic trajectory can take. On the right-hand side, if you look at the right-hand side, there's a delta function missing here. So I have to write that here. We've got delta here. On the right-hand side, you have this delta function. Here you have this delta function. And this delta function just makes sure that whatever we integrate here, whatever trajectories we integrate over, that they fulfill the discretized version of the Langevin equation. Yeah, so the delta function is just the left-hand side minus the right-hand side of this Langevin equation. And if the left-hand side is equal to the right-hand side, then we take that trajectory into account. Yeah, and then sandwiched between that, we have our observable, O, that is some functional of our trajectory x. Now, as I say, functional, so I don't know how much functional analysis all of you had. So so I would expect that most of you would have that until the fourth term or so. But just to make sure, a functional is basically a function that maps that maps this function x that maps a function to a real number. And this is how we define these observables. You take a trajectory and you map it to a number. Okay, so this looks very complicated. It doesn't help us anything at all. And one other step we need to make on the slide is that we introduce some notations here. And of course, we don't always want to write all of these integrals here on the left-hand side. We just say we write that in this functional form here. And of course, many of you will know that this is just a functional integral or a path integral. That's how we define it here. And now for notational convenience, we just go to a continuum notation. Now we forget that we discretized time in the previous step, and we write the equation back in a continuous form, just for the sake of simplicity. And we define some delta functional that is just equal to the product over all delta functions that we had on the previous slide. Now, if you look here, the product over all delta functions, just make sure that you fulfill the Langevin equation really at each time point. And we just define like a super delta function or delta functional that makes sure that we really satisfy the Langevin equation at each time point. So now we make a little trick. We say we have this delta function, this product of delta functions. And what we say is that in Fourier space, the delta function is represented by a plane wave. So we Fourier transform the delta function. Or a functional is now. And the Fourier transform of the delta function just becomes delta of x dot minus f of x minus psi. So our delta, our Langevin equation is equal to a Fourier space d x tilde e to the minus I x tilde x dot minus f of x minus c. Now we now get this variable x tilde. So this is nothing happened here. It's just the definition of the Fourier transform of a delta function. And because we had this product over many delta functions here, we have the integral here, the path integral here, we also get a path integral delta x tilde. So that's just the definition of the Fourier transform. And now we plug this in again. So we obtain from that the expectation value of our observable, taken to the average. Now this average is over the different over different noise realizations. This is equal now. We plug that in. An integral now over x and x tilde. So it's a path integral over x and x tilde. So there's an integral over all realization of x and all realization of x tilde. So now this x tilde pops up. So we don't really know what it is, but it will hang around, and I will show you later what it actually means. So we have this path integral, so our observable O of x, and then plugging in e to the minus I x tilde. Sorry, I've got an integral. So we have here a little integral dt. And this integral we get because we had this product over here. Now, so here the product we had here gives us an integral, so our sum in the exponential. So this was originally like a product of many exponentials. And so this is this, and then we have our x tilde, x dot minus f of x minus xi. Yeah, and then we close the average, and then we just plug this in. Yeah, we can move out everything that does not depend on psi, of the noise, out of the average, because the average is over the noise. B x tilde power of x. It now comes the stuff that does not depend on x, on the psi. Integral dt x tilde x dot minus f of x. And now we have some average over minus I dt x tilde times psi. No? So now the question is, what is this here? Can we calculate this? Now, at the moment, we cannot do anything with this equation, with this expression. Can we calculate this last term that involves a noise average over e to the minus dt psi tilde and psi? Yeah, and there's hope that we can calculate this because we know what psi is. Now, we said that psi is a Gaussian random variable. Yeah, it follows a normal distribution. It's uncorrelated, so we know a lot of things about this psi. And what we'll do right now, yeah, because psi is Gaussian, there's also hope that we can actually solve or integrate this integral that is this average here. Now, I'll show you now how this works in detail. Yeah, so we make use of the definition of phi. So let's see what this second average looks like. Now that's O of x. Sorry, it's not O of x. It is e to the minus I dt integral x to xi. Yeah. And this is, by definition, the definition of the average, is equal to the integral over the xi times the probability over the probability distribution of psi, which is a Gaussian or a normal distribution, 2 pi a. A is the strength of our noise, e to the minus psi squared over 2a. Yeah, so this is the probability distribution. If we know that psi is normally distributed, and that's why we have this normal distribution here. And now we multiply this by the thing we're averaging over. Yeah, e to the minus I dt x tilde psi. Yeah, so this
excuse me.
Yes.
Isn't it supposed to be exponential plus psi integral delta t whatever?
Integral over, let me see. You mean the second integral, this one here?
Yeah.
Okay, so this one is that minus or plus. Let me just check. Let me check my notes. Okay. So here we go. So no, there's a minus. I wouldn't be able to find them. I wouldn't be able to find it.
On the previous slide, you can go and just.
Okay, so let me see. Maybe there's a. So here we have the minus. Here we have the minus. Here we have the minus. Here we have the minus and another minus. Yeah, you're right. Let me see what's wrong here. Okay. Yes, okay. So here, I think this minus here is not right. Yeah, that's just the definition here. Wait, minus, let me see, let me see. Okay, minus with plus. Minus with plus. I think you're right. But then here should be a minus. So where does is there an I squared somewhere?
Excuse me, I think
yes?
there should be a minus sign in the first exponential as well. In the last step on this particular slide, there
Here?
are two exponentials.
Yes. Yes. That's what I'm wondering about. Let me see if it's actually in the final result. Ix minus. Okay, so Mike, let me just see. Let me just see. So let's put this minus here in brackets. Yeah, so this one minus, this should have the opposite. Oh no, wait. Okay, this is the minus. No, then this should be plus, you say? Yeah. I think it will come out correctly later. Now let's see how it goes. Let's see how it goes. Now it makes sense. Now we have to have a Gaussian integral. Yeah, and that will determine whether what we're doing is right. Okay, so let's go on. So this here is the integral. And now we just put everything together and say that the xi 1 over 2a e minus dt x tilde psi. Now that's the first one, so that would be a plus then. Minus I dt x tilde psi. Now I just combined the exponentials. Now thanks for paying so much attention. So yeah, and this is here a Gaussian integral. And if you don't remember the Gaussian integrals, and you can look at the bottom here, these Gaussian integrals are pretty easy to solve. Probably most of you have heard of that. And we can also solve this Gaussian integral here. And what we get is that this is just e to the a over 2 dt x tilde squared. Yeah, because we know. Yeah, and here one thing you have to make you need to remember is that this here has i's in it. Now, if you look at this formula at the bottom, you need to take into account that these are complex integrals. Yeah, so we can calculate this quantity here. We can calculate this quantity here because we know how psi looks like. And then we integrate over the distribution of psi, of the noise realization, and we get the term that we have here. Yeah, and now we already have arrived at a famous formula, at least famous for a very small number of people. And this is the so-called Martin Sittler-Rose-Johnson-De Dominicus functional integral. Yeah, that's what you see here in the red box. Now we just now put everything together. Here we have our noise. Here we have what we had before. And here is, so to say, the deterministic part that came from the Largemont equation. Yeah, and so what this tells us now here, and maybe it looks familiar to some of you. If you had quantum field theory, this looks very familiar. So what we do now is we want to calculate the average over some observable. We integrate over all possible realizations and over all possible realizations of some weird quantity x tilde. So we got a second field here. And weight the contributions of different trajectories by this exponential factor here. Now, and this exponential factor looks very much like what you know from other field theories, like quantum field theory. And this is why this is very often called an action. Now, that's the Martin-Sydra-Rose, or MSRJD, functional integral, and it allows us to really write a field theory for stochastic processes. Now, so here our axes are not fields yet. Now they're trajectories. They don't have a space component. Now they don't have spatial dimensions. But as you will see later, the structure of a real spatial field, the integrals, they will look very similar. Now, we can also rewrite this a little bit and look at specific trajectories. And then we can look, for example, at a special case where this observable is just the propagator here. Also, propagators is the probability that we end up at some state x at a time t if we started at some x naught at a time t naught. And we obtain this by just requiring that this observable is a delta function, where we say that the x, the specific time t at a time t, needs to be equal to the x that we give to the probability distribution here. And then we plug that in. And what we now need to say is that we only integrate over trajectories that actually start at x naught and end in x at the given times. Now that's what we have to take into account for in the boundaries and the bounds of the integrals. And then we get this form here. Now that looks very similar. And that's a different representation. If you remember last time, we had the Chapman-Kolmogorov equation. It was an equation for the same quantity. And the idea was a little bit similar, right? So in this Chapman-Kolmogorov equation, we had the same spirit. We looked at we summed up different paths a process could take to get from x naught to x. And here we do the same thing in a more fancy way. So just to reflect on this a little bit more. So what happened now? So we started here with a Langevin equation. We discretized it. And if you remember quantum field theory, that's also the step that you do there. You discretize time into small intervals. That's the first step if you derive the quantum field theory. And then we wrote expectation values of some observables formally in a way that involved integrals over all possible trajectories, and then we filtered for trajectories that solve the Langevin equation. Now that was, so to say, circular starting point. And in the next step, we then got this field psi tilde. Now that we still don't know what it is exactly about. Now we got that from the Fourier transform of the delta function. And now we have two fields. We integrate over two fields, x and x tilde. And in the end, we managed to integrate out the noise. So what we have here now is something that does not depend on the psi anymore. So say it's a deterministic equation and deterministic integral. So somehow our noise was absorbed into a new field, a new fluctuating field, x tilde. And that's how it very often goes. Now that you make a field theory, and what you gain is you get some nice integral, but you have to pay for it by having additional fields, conjugate fields that you have to integrate over. And the same is true here. And I'll show you later what these x tilde actually mean. Before I do that, let me just mention, so now we have a field theory, we have a path integral. And these path integrals are very useful because we can make use of a lot of tools from other field theories, from quantum field theory, like renormalization, perturbation theory, and so on. We can make use of these tools, very powerful frameworks developed in the last 70 years or so. We can make use of these frameworks and apply them to these field theories for stochastic processes. And one of the things that we can do is we can define a so-called generating functional. That's maybe something that you already know from other field theories. So what you do is you add some auxiliary fields, external fields, H and H tilde. And these fields couple to X and X tilde, the auxiliary fields respectively. And what this is then the generating function. And of course, we know that these fields don't really exist. Now we just added them. And the reason why we added them is that if we take derivatives with respect to these fields, H, or these external forces or external fields, H, here and here, what will happen is that each time, because this is an exponential, the X, or well, let me just draw that, the X or the X tilde will go down here. And if we do that, if we take these derivatives, so we can therefore get expectation values of combinations of the X and X tildes just by differentiating this generating functional with respect to these weird virtual fields. And when we've done that, we have to remove these fields again. So we have to set them back to 0. For example, if you want to have the correlation, the autocorrelation function, so how much is the process at a time t correlated to the state at a time t prime, then we differentiate, then we take the derivative first with respect to h at a certain time t, and then we get one of these x's here, and then we take the derivative with to h at a different time t prime, and then we get the field again at a different time here. And these are of course functional derivatives. That was functional calculus. If you haven't done that, it's for these, what you do is you look at the change of a functional. Now, for example, this here is a functional. You look at the change of a functional with respect to small changes of its argument. So you look at perturbations in h and h tilde around some value, and then you see how your functional changes. That's called a functional derivative. And if you do that, you get very conveniently these prefactors here, right here in front of the action. And if you look at the definition here, this is just what gives us our observable. So for example, if our observable is x, then we just take the derivative once, we get an x here. And if we have the x here, we have the first moment, so the mean of x, the average of x. If we take the derivative twice at different times, then we get a correlation here on the left-hand side. So this is a very convenient tool. And as I said, if you want to have a correlation function, for example, we take the derivative twice, and you must always remember to set these fields to 0 again. It's actually the same approach as you do in the quantum field theory and classical field theory, the equilibrium field theory. Okay, so now what is this x of t? That's just a remark, so I'm not doing the calculations live. What is this x tilde of t that we got in this process? There are different field theories for stochastic processes and for master equations, and you always get some kind of auxiliary field, some conjugate field that you have to pay for. And this x tilde from here, you can get an intuition about that. Not super rigorous, but you can get intuition about this. If you write down the master equation, the Langevin equation, with respect and add some external source, capital H of t. Yeah, and if you add this external force, capital H of t, some temporally fluctuating force that doesn't depend on x itself, and you plug that into this Martin-Sidger-Rose functional integral, or Martin-Sidger-Rose Johnson-Didyminicis, then you see a formal analogy that if you you get a term that looks like H tilde. If you define this to be minus I, this external field. Yeah. And now we can see what happens to x. What is the effect of this external field, H of t, on x? So there's a little bit in an analogy already here. Now, so here on the left-hand side, it has something to do with this external field from the generating functional that couples to x tilde. Now let's see what this does to x, to the actual stochastic process. And to this end, we calculate a response function. And this response function is just the change in the average of x with respect to changes in this external field. And that's called the response. So how does the system respond to changes in this external field? Yeah. And so as you remember, the average here, we just get by integrating, by taking this generating functional and taking the derivative with respect to h once. So that's the first moment. And because of this equality here, we see that this here, this response function is, we also get that if we take the derivative with respect to h and then h tilde at a certain time t. Let me see. Let me just say here. That's the tilde. Yeah. And this here, what this is, as on the last slide, is the correlation between x of t and x tilde of t. Now, somehow the response of the system with respect to an external force or an infinitesimal external force is given by how the x tilde couples to x. So it describes the x tilde, or is related to an infinitesimal response of x, of the field x, with respect to a small perturbation. And that's why this field x tilde is also called the response field. Yeah, just a little bit of intuition, and very often these conjugate variables somehow in some way encode the noise. Yeah, now I have an example. Let me just check the time, whether we do it now or at the end of the lecture. Let's do it at the end of the lecture again. This example, for those of you who heard the field theory course last year, they will know the example. So I'll leave that to the end of the lecture, that people can dial out if they're tired. Now I want to just give you a second remark. So we are now in the framework of field theories. And in field theory, if you remember, we can have different formulations of field theories. In other words, the Lagrangian field theory and the Hamiltonian field theories. And we can translate these two into each other. And we can do the same things here for the non-equilibrium field theory, for the stochastic process. Yeah, and it's also just a remark. It's not so important for the rest of the lecture, but you can formally define new variables Q and P by these relations here. And then this probability will take the form that I wrote down here. Yeah? So this has formally the form of a Hamiltonian action, or having a Hamiltonian theory. So we have P times Q dot minus some Hamiltonian, and this Hamiltonian is given by this term here. And this looks a little bit like a kinetic energy. Yeah? So it's just saying that we can write by variable transformation, we can write these field theories that quite analogously to field theories that we already know. And we can even go one step further. We can take this here and integrate out the p's, because it's just quadratic in p. So these are just essentially Gaussian integrals that we can integrate over them. And just to tell you the results, we then get a field theory that looks like a Lagrangian field theory. Now we have a Lagrangian that depends on Q and the derivative of Q with respect to time. And if you then look at the analogy at this Lagrangian here, then this looks like it describes some kind of particle that has some mass 1 over a, that lives like in a potential that's coupled to some Q dot here. And we have now here the quadratic potential as the last term. So now these analogies, they're not very helpful. Yeah? They don't tell you anything. These Hamiltonians that you get here, they're not comparable to Hamiltonians that you get in quantum systems. Yeah? So for example, these Hamiltonians, they're not Hermitian. So this is a weird quantity for quantum physicists. Yeah? Just to say that there are different ways of formulating these field theories that you get by variable transformations. This second equation here has a name, that's the Ohm-Sagar-Maklov functional, and you will pop up these kind of functionals pop up in papers. If you read papers, they pop up in different ways, but in the end, they're the same implementations of a field theory implementation of the same stochastic differential equation, but just reformulations of the same thing. Okay, now I told you in the beginning of the lecture that actually what we're in most of the cases interested in, and what field theories are also good for, are spatially extended systems. Now, how do you write down a Legendre equation for a spatially extended system? Now it gets, of course, a little bit more complicated, but there's actually a classification scheme for a Legendre equation that describes systems that have spatial degrees of freedom. And this classification scheme you can see on the slide. So we're looking here at some time evolution of some field phi at a position x at a time t. And this time evolution is given by different components that are on the right-hand sides. On the very right, we have the noise, as always. And this noise has the usual properties. So the average of the noise is 0. And it also has correlations. So how is a fluctuating force of that psi represents, how is that correlated between different time points? And how is that correlated between different positions in space? So while the assumption that different correlations, that this noise is uncorrelated in time, so that you don't have memory, is something that is very reasonable and that we typically make, it's not so clear that the noise is also independent at each position in space. So generally, there will be some some length, you perturb the system, and then you don't perturb a single atom, but you perturb like a small region, for example, and then these fluctuating forces are correlated over small regions. And these correlations in the spatial in these spatial systems, in the fluctuating force that act on these systems, are given by a so-called spatial correlation kernel. Now, that just says how are these fluctuating forces, how are they correlated between two given positions in space. And now we have the rest here. The black parts here, it's just a fancy way of writing down the deterministic part of what's actually happening. And it's just a fancy way of writing down the actual, for example, chemical reactions that change the value of the field at a given position. And we can formally write down this this term by saying, okay, so we have some kind of potential, and the dynamics will go so to some minimum of this potential, to some attractor, some equilibrium state. And then we can formally write this way here, that we have some functional, some free energy functional f that depends on the fields. And this is given by some space integral where we have this term here that will flatten the field. That's something like can become a diffusion term. And on the right-hand side, we have something that is a potential that describes what's actually where we're going to with the field. Now, if you have heard statistical physics, then these will look familiar to you, like 5⁴ theory, Ginzburg-Landau, and so on. Now there's this red stuff here. And this red stuff is just a way of classifying different kinds of systems. And people distinguish between systems where the order parameter, so our phi, is not conserved. For example, in chemical systems, where you can convert one chemical species to another chemical species, and then another chemical species, and so on, then the concentration of one chemical species is not conserved in the entire system. And this is what you get if you set this exponent to 0. That means you don't have this Laplacian, the second derivative here. The other case is when you have set this to 1 here, set this n to 1, then this will here be part of something like a diffusion term. This will go into a diffusion term, and what you will then get is what these kind of systems that describe are situations where the field, so phi, is conserved. So you remove stuff at one point of the system. If you remove stuff at one point of the system, it has to pop up at another point. An example is, for example, if you have something like hydrodynamics, also where you just move mass around, and but it doesn't really disappear. You just move things around, but things don't disappear. That's an example for these kind of model B systems. And so if you plug these things in, so typical examples, very famous example of these systems are so-called reaction diffusion systems. So, and the typical reaction diffusion equation is seen here on the right-hand side. That describes a situation where the phi, if you look here at the phi, then what happens, what this term here does, is if phi is just a little bit larger than 0, then this term will be positive. And this will give to rise an increase in the field. Now, this term is a diffusion term that just transports information, so to say, between different positions in the system. And then we have our noise, and this noise typically has prefactors, it's multiplicative, if you look, for example, at biological systems. So at the take-home message for these spatial systems is, now you can think about, okay, we just add an x variable. What I just said is just a complicated way of saying, okay, so we have some x variable, and some diffusion, yeah, but everything else will look very similar as before. Yeah, and indeed, we can follow exactly the same steps now. Now we take the Langevin equation, general Langevin equation here, you know, which is this one, and do exactly the same steps as before. And now this here would be the first step. Yeah, where we have this delta function. Now we don't only have the product over I that is already in the over time, that is already in this delta function here, but also over X. Yeah, and then we just plug in this generalized Langevin equation and do the same step, and then we get the field theory, the Martin-Citro-Rose functional for the spatially extended system. So this looks pretty complicated, but it is actually the same as before. Yeah, so we integrate again over the field phi and the response field phi tilde, and then we sum up different contributions to our observable, that's the second term, and then as before we weight that with some exponential that essentially quantifies how far we are away from a realistic realization of the Langevin equation. Yeah, and here we have exactly the same structure as before. Here you have the Langevin equation. Now you say that you need to solve the deterministic part of the Langevin equation. And this was previously just x tilde squared. So previously, this term here was something like a over 2 x tilde squared. Yeah, now that looks more complicated, yeah, but it has the same form. Yeah? If you look at this, you have here your x tilde or phi tilde. Here you have another one. They're just coupled by the correlations in the noise that is described by this noise kernel. Yeah, but the structure is the same as before. Yeah, and so this is the Martin-Citro-Rose functional for the noise, for the spatially extended system. Yeah, and with this, I'm done with the definitions and with the actual derivation of the field theory. Now let's see if we can apply it. And now I go back to the example. Just see how we're doing in time. Okay, great. Almost exactly an hour. So if you already know all of this, maybe from last year's lecture, then feel free to drop out. And for the rest, I'll go through one example. And I'll double check. So if when I upload the lecture notes, I'll try to make sure that actually these minus signs are correct. Yeah, so if there was a mistake, I'll correct it in the uploaded version that you find on the website.
Excuse me.
Yes.
So when you wrote the response function, there was this, I guess, Heaviside function multiplied with
Yes.
your autocorrelation. So does that come up because you have kind of the ethoformalism into your system, the point of integration?
You can think about it physically. Yeah, the response function, if you have a perturbation here, so if you perturb at t prime and you look at the response at t, yeah, that's how this response function is defined. So I should have here, that's a t prime here. Now, so you perturb at t prime and you look at a time t. Yeah, then, or the other way around actually. Yeah, so then this Heaviside function just ensures causality. Now, you cannot observe a response that happens before you do the perturbation, before you apply the force. Okay. Yeah, so that's the reason why you get these theta functions.
Okay.
Okay, thanks for the question. Let's go then to the where's the example? Here we go. Yeah, and so let's have a look at the field theory for a very simple example. And all like in stochastic processes, also simple examples quickly become complicated. So let me find the notes. Here we go. Okay, we start with probably one of the simplest Langevin equation you can imagine. And because it's so simple, it has a name because it has been extensively studied, and it's called the Ornstein-Uhlenbeck process. And this process is just given by the time derivative of x dot, and this is equal to some restoring force here, so plus some external fluctuating force psi. And as always, we have the usual conditions that psi is very nicely behaved, doesn't have a mean, and it's uncorrelated in time. So now, writing down the Martin-Sidger-Rose functional integral is easy because we just have to plug in this Langevin equation. So the Martin-Sidger-Rose, Johnson, the Dominicus. Some people say Martin-Sidger-Rose, but I did that once, and I happened to be in Munich, and then they were very angry that I forgot Johnson, who apparently had some connections to Munich. And so that's the full, that contains, I think, everybody who contributed. Reads, so what is the action now? I don't write the full integral, just write the action. So the action is dt I x tilde delta x plus alpha x. Now that's make sure that we fulfill the Langevin equation, plus a over 2 dt x tilde. Now that should be squared. Now we can write down the generating functional. Generating functional. And this is just as before, z of h tilde is equal to the integral over our two fields, functional integral over our two fields, field and the response field, e to the minus s plus dt h x, so the external auxiliary field that couples to x, plus an external field that couples to x tilde. And just to make sure everybody understands. So why do I say that these fields couples to x and x tilde here? So these and why are these external fields? If I write it like this, this just follows if you write down something like, for example, the Ginzburg-Landau theory or so, or you look at the Ising model. Then terms like this here will tilt the potential in one direction. And here, this tilts the potential in the x direction, and this tilts the potential in the x tilde direction. This tilts it in the x direction, and this tilts it in the x tilde direction. So this is why we call this external fields, and that they couple to these fields x and x tilde. It's just the analogy to the Ginzburg-Landau theory and other field theories. Okay, so let's go. This is the functional, generating functional. And now we use that integral over dx e to the iqx is just delta of Q. So we use the definition of the Fourier transform of the delta function. Yeah, and by doing that, we get that this functional generating functional is equal to d of x tilde e to the a over 2 integral dt x tilde squared plus dt our two fields hx plus h tilde x. Yeah, and now we got our delta function I del t minus alpha x tilde plus h. Yeah. Now, when is this delta function here, this delta function, actually non-zero? No? So the delta functional is non-zero if our x tilde solves this ordinary differential equation, that we have here in the delta function. Now we can just write it down. I times t to infinity dt prime e to the minus alpha t minus t prime h of t prime. Yeah. Now we substitute that. So we saw that we already got rid of one field here by doing this reverse Fourier transform. Now we substitute that and we get rid of our second field. Now we substitute into z, and what we get is h tilde is equal to, and now comes a large exponential, to see how to write that on the screen, minus integral dt integral dt prime. Now that's the second, it comes from this x tilde, and then we have a over 2 e to the minus alpha t minus t prime times h of t prime plus I theta t minus t prime e to the minus alpha t minus t prime times, sorry, I said it like even for the simplest process it gets lengthy, h of t prime. Yeah, but what is happening here is nothing magical. It's just a calculation. It's just integrals. Yeah, we substituted that x tilde into our generating functional, and then we collected the terms and made sure that the right time order is given. And now we have this generating function. It looks a little bit complicated, but we can deal with that. So we can take functional derivatives with this. For example, to get the correlation function, so we have x of t, x of t prime. Now we take the second derivative once at time t and once at time t prime. And then we must not forget to set the fields equal to 0 again. Yeah, and if you look at this equation, if we do that, then and do a little bit of calculations. So we get that it's actually this correlation function is a over alpha e to the minus alpha t minus t prime. So that's just an example. Yeah. So these actual calculations are a little bit messy, but that's just how you use these field theories. Yeah, you have the field theory, you write down the general functional, yeah, and then you look that you're able to take these functional derivatives with respect to these external fields. And the rest is then, so to say, mathematics. Yeah. Okay, great. So this was an example, and from next week on, we'll be a little bit more intuitive again. Now we've covered the technical stuff, and we can look into some real physics problems. Okay, see you all next week. Bye.